Hello everyone! In this video, I'll be giving you an overview of how I created a Pac-Man clone from scratch, written in C without using an engine. I really wanted to make this video as a way to demystify how some of this stuff works and what the steps were that I took to create a game in this way. When creating games from scratch like this, there's actually a few things that need to be set up before we can start working on the game itself. The two primary things that are needed initially are a window that will be used to display our game in and a message loop. Since I'm using Windows as my development platform, I set both of these up using the Win32 API, which is a standard part of the platform itself. So the window itself should be pretty self-explanatory, but you might not be familiar with what a message loop is. A message loop, which is sometimes also referred to as an event loop, is essentially a way for us to process messages that we receive from the operating system. There's many types of messages that we might receive, and we can specify special behavior for the ones that we're interested in. Just to give you an idea of what some of these messages may look like, for instance, we might be informed by the OS that the user has moved their mouse around, that the window has lost focus, or that they dragged and dropped a file on top of our window, just to name a few. There's a whole bunch of these message types, but in my case I was really only interested in a few of these, such as a message telling me when the window is created and when it's closed, and if there's any keyboard input. So the window and the message loop are two elements that are pretty much always required for programs that display graphics in some way. If you use something like a game engine on a PC, you typically don't interact with these parts directly, but they do exist somewhere behind the scenes in the engine code itself. Here you can see the base structure of our game. We start out with initializing some subsystems that we need. In our case, we create and register the window here. Then we process all of the messages on the queue and listen for the ones we're interested in, which in our case are things like keyboard input and a quit message to inform us that the user has closed the window. We also receive messages that we don't really care about, and we simply forward those to some default Windows routines that handle them internally. Once we've processed the messages, we run an iteration of our update loop where we handle all of the logic in our game. We then render a single frame of our game out to the window. Finally, we move back to the top of the loop and the process repeats itself. This goes on infinitely until we receive a quit message that we use to exit out of the loop. Once we've exited out of the loop, we run some cleanup code to get rid of any resources that we created before reaching the end of our program. After I had set up the window and the message loop, I moved on to creating the renderer. The renderer itself is done in software, and the idea here is that there's a block of memory, which we call the frame buffer, that is going to be used to write individual values to, which will represent the final RGB values of a certain pixel on the screen. Once we've written out all of the pixels in our frame buffer for that particular frame, we need some way of displaying them onto the screen, because at this point they only live in memory. In Windows, there are several ways we can do that. The method that I chose to go with was by using Opengl to copy the contents of the frame buffer over to an Opengl texture and drawing a single textured quad to the screen. Drawing the quad to the screen is really the only Opengl drawing command that is used here, as the actual rendering is done by writing individual pixels to the frame buffer. One problem with Opengl on Windows is that only version 1.1 of it ships with Windows, which was, according to Wikipedia, released in 1997. This is essentially the Stone Age in the world of computer graphics. However, we can still get a newer version of Opengl by asking the driver for it and loading extensions for any functionality that is not exposed by the default implementation on Windows. The way Opengl is initialized is by creating something called the Opengl Context, and doing this is actually different per platform, so for that reason, most people will opt to use a library such as GLFW or SDL to do that. But since this is a from-scratch approach, I wanted to write this myself and avoid having to introduce any dependencies to the codebase outside of the stuff that is shipped with the platform itself. So in order to initialize Opengl on Windows, you need to do this using something called the pixel format descriptor, and as the name implies, you use it to describe a format that you'd like to use. You can think of the descriptor as the properties you want to have set for your context. So things like the amount of bits for your depth buffer, whether you want to use hardware acceleration or not, if you want to use single or double buffering, and a whole slew of other options. Once I had this in place, I wanted to quickly verify if I had set up everything correctly. And I wrote a quick test using old school immediate mode to see if I would get anything onto the screen. I wrote some randomly generated color values out to the frame buffer, which resulted in this mess. And I'm not even sure if YouTube's compression will handle this nicely, honestly. But anyway, now that I had verified that this was working, I moved on to initializing a more recent version of Opengl by essentially asking the driver for it and loading extensions, as I mentioned previously. In order to do this, the GPU itself needs to actually support the version of Opengl that we're asking for, otherwise it will simply fail to do so. In all honesty, there's absolutely no reason why I'm doing this for this game, as I'm technically good to go with the 1.1 setup. However, I did this because I wanted to satisfy my own OCD, and it simply doesn't feel right to use the old fixed function style Opengl in 2021. Setting up a modern version of Opengl to get the same results actually requires quite a lot of boilerplate, as you can see here. And also note that this does not even include the extension loading for the newer version, so it's even more code than what you're seeing here. Anyway, at this point I had most of the boilerplate out of the way, and I wanted to actually draw something onto the screen that wasn't noise. To do that, I had to summon my inner Bob Ross to create some happy little pixel art onto an image. However, I had no way of actually drawing an image at this point, so the next thing I had to do was writing a bitmap loader. I decided to go with bitmap as the image format of choice here, because it's one of the more simple formats out there and it's not too difficult to implement. There are some dumb quirks with it and different header versions, and I have to admit my implementation is the bare minimum of a loader, but it was good enough because it supports everything that I needed to load the graphics for the game. As you can imagine, while I was implementing this, I ran into some weird offset and byte padding issues, but I was thankfully able to sort it out after some debugging, as you can see here in the memory viewer, where we can see our little dude in all of his in-memory representation glory. I also had this weird streaking effect going on once it worked, but that was because I forgot to clear the pixels back to a default color at the start of every frame, so that was a pretty simple fix. Now that I could load bitmaps, I created some more pixel art, this time of the ghosts, and I placed them all onto a single texture atlas. I wanted each ghost to look slightly different and not be a palette swap like they are in the original Pac-Man, but after I had drawn all of them, I realized that none of them actually looked like ghosts. I was still okay with this because I was honestly too lazy to redraw all of them. Once I added the first sprites to the texture atlas, I had to create a new drawing function that could draw a portion of the texture that I passed to it. I did this by supplying it with a rectangle that contains the coordinates of the source sprite on that texture. I ran into some weird results while I was implementing it, so I had to spend some time debugging this as well. But eventually I was able to fix the issues that came up and get it to display the correct results. I then drew the player character and decided that he needed to look way more menacing than the original Pac-Man, so I figured it would be fitting to give him fangs as part of his new look. With the texture atlas drawing routine in place, I could now utilize that functionality to flip between the two keyframes that I had drawn to create this animation and draw him to the screen. At this point, I had most of the stuff in place that I needed and could finally move on to implementing the actual gameplay itself. I first started out with capturing user input that I obtained by reading them from the key up and down messages in the message loop. Once I had that, I implemented some very basic movement which I used as a starting point. This was just a quick way to test if my input code was working correctly. Once that was up and running, I updated the player character to keep track of the last direction he was going in, so that I could use that later on as a way to create the auto movement that Pac-Man is known for. I then added a single wall to stop the player's movement whenever they would run into it. The next thing that I wanted to do was to correct his path. What I mean by this is that since Pac-Man is a tile-based game, as many games of the same era were, the entire level is essentially aligned to a grid. In the original game, whenever Pac-Man or one of the ghosts move around, they are always sort of locked to either the X or Y axis and can only change their direction whenever they're in the center of one of the grid cells. To explain this a little better, here you can see some valid locations that Pac-Man can be located at on the grid. As you can see, he can be unaligned on one axis at a time, but not both at the same time. So you couldn't end up in a location such as this, for instance. This was the next thing that I added, and I started out with some hacky correction code whenever he would bump into a wall. It looked pretty bad, but it was only used as a starting point to eventually keep him locked to one axis. As expected, whenever you're dealing with collisions in games, there's bound to be some weird shit going on, and I also ran into some weird effects while implementing this. After some time spent tinkering with this code, I was confident that I had it working correctly. You can see me test it here, where it looks like I was doing some sort of ritual dance to summon a demon or something. Even though I was pretty sure that it was working, it was still a bit difficult to verify if it actually worked or if my mind was playing tricks on me. So, in order to get a definitive answer, I figured I should actually visualize the game's grid in some way. I leveraged what I had and simply filled out the background with repeating red ghosts to visualize the game's grid. With the weird grid in place, I could now clearly see that it was working as I hoped, and that it only allowed me to change in a 90-degree direction whenever I'm in the center of a tile as I move around. The next thing that I worked on was adding support for wrapping around the map if a character goes off screen. I actually realized that this wasn't going to play nicely with how I was currently handling collisions, so I started working on handling them gracefully in these situations. This was honestly something that was a bit nasty to get right, and I ran into quite a number of issues. It took some trial and error, and I think this was one of the areas where I spent the most time on. But I eventually got it to a point where I was happy with how it turned out. However, I then took a step back and realized that this situation should never even happen in the first place. Wrapping around the screen in Pac-Man should only be possible if you can actually end up on the other side of the screen. So it makes no sense to wrap around and then have something blocking you immediately. Because of this, I decided to not spend any more time on this code and get rid of it entirely, so that I could focus on the next thing, which was implementing the level. Since this is a tile-based game, I implemented the level as a 2D array with a fixed width and height. I also created an enum that specifies the different types of tiles, such as walls, pallets, and the starting positions for the characters. So with this approach, all I had to do was fill out each individual index in the array to create a level. Tile-based games lend themselves well to this approach, and it becomes really trivial to quickly change things around and experiment with levels. Now that I had the basic level data structure in place, I linked the sprites on the atlas up with the drawing routine and experimented around with some level designs. My levels were honestly all garbage, so I decided to essentially copy the original level in Pac-Man, which looked a lot better than any of my own attempts. There was a problem with this approach, however, and it had to do with the fact that I was using a different aspect ratio than the original and had a different number of tiles as well. What that meant was that there wasn't a one-to-one mapping between the two, and this is especially obvious near the bottom, where I simply couldn't put the bottom row of walls there as I ran out of space in my 2D array. This problem can of course be easily mitigated by implementing scrolling graphics and having a larger array. But I wanted to keep it simple for now, and instead I eventually took some creative liberties later on and changed some of the level around so it could fit nicely into this array. At this point, I was starting to feel like it began to resemble the original, and the next logical step was to add the ghosts in. I started out with only adding one ghost and getting the basics up and running before applying it to all of the ghosts. One of the first things that I did here was move some of the player-specific code out into its own slightly more generic routines so that I could leverage the same movement behavior for the ghosts as well. This was really nice because now I didn't have to duplicate or rewrite too many lines of code. Simply put, I wrapped some of the common data between the two in a struct that I called game entity, and I created two more structs, player entity and ghost entity, that contained unique data and an instance of game entity. I personally like this approach a lot, where I avoid abstracting things too early and only do so when it starts to make sense, such as in this case. I find that it prevents me from making the wrong assumptions early in the process, and that it helps me write better abstractions that are actually helpful instead of being over-engineered and unnecessary. Next, I moved on to creating the ghost's behavior, but I didn't actually know how the AI for it worked in Pac-Man, so I googled around a bit and eventually stumbled upon this video by Retro Game Mechanics Explained. The video goes into great detail of how the behavior works for the ghosts, and I won't explain too much as to how it works because the video already does a terrific job at that, but the main takeaway here is that the ghosts essentially have 4 states that they can be in at any point in time. There's the chase, scattered, frightened, and eaten states, and they're all pretty much self-explanatory as to what they do, but in the chase state, the ghosts have slightly different behavior that is unique to each one individually. Because all states share some common behavior, I first worked on the way the ghosts handle pathfinding and added a way for them to target a specific tile. Deciding what tile to target depends on what state they're in, but behind the scenes the logic for reaching their destination is always the same. I implemented most of their behavior based on their behavior in the original, but I left out some quirks such as overflow bugs and different timings based on the level. But for the most part the behavior should be pretty similar. Eventually I had the scattered and chase states implemented, and it was time for me to implement the last two states, the frightened and eaten states. Both of these weren't too difficult to create at this point in time because I already had a lot of what I needed in place. The only thing missing for the eaten state was the ghost house itself, so I added that in at this point. I also made sure that the 3 ghosts that start out in the ghost house leave the house after some number of pallets are eaten by the player. The frightened state was really straightforward to implement. The only thing that I needed to change was the way they determine the next tile to target. The difference here when compared to the scattered and chase states is that they choose a random direction whenever they reach a new tile. The only exception is that they can't move backwards, but aside from that they can go in any valid direction. The very last thing that I added was a simple way of resetting the game whenever the player would run into a ghost if they weren't in a frightened or eaten state. At this point, the core elements were all implemented and I decided to wrap it up. There's of course still quite a few things that could be added to polish things up. Some smaller things like the fact that Pac-Man always faces the same direction, which makes it look like he's moonwalking all over the place. But also some larger things, such as the fact that nothing happens whenever you clear out the entire screen of pallets and end up in this limbo-like state where the game keeps running. There's also no menu or a way to actually pause the game, which would be a nice thing to have as well. I might address some of these shortcomings in another video, but for now I think the end result shaped up quite nicely. Thank you for watching, and I hope you enjoyed this overview of creating a simple game from scratch in C.